So, an introduction to benchmarking then. One of the most important things when you're benchmarking or performance testing your application or your runtime or whatever is that you should change one thing and one thing only. This might seem quite obvious, but the thing you should change obviously is whatever it is you're wanting to work out the performance of. So if you've just gone and checked in a new copy of your application code and you're wanting to know does it perform as well or better than what it was doing previously, you'll be keeping everything else the same. So you'll be running on the same version of Node, same machine, using the same set of NPMs, same versions of those modules as well, and just be changing your application code. It can sometimes be quite tempting to go and change everything at once. So you just released version 2 of your application, and you think, actually, yeah, and also we'll go and update the version of Node that we're running on. We'll go and update to Node version 6, and we'll go and put it on this brand new machine we've got, and we may as well go and pull in all the latest versions of all the modules. That means that it's quite difficult to decide whether there is actually a performance regression or not. You could just be masking a performance regression by an increase in, for example, the speed of your machine that you're running on. Something else that's worth mentioning is that performance testing and benchmarking is quite different to functional testing. In functional testing, typically, you'll do your run and it will either pass or it will fail. And if it fails, you can maybe rerun it and it might work the next time. With performance testing, it's not only whether the run completes or not, but you're also going to be interested in whereabouts the data is in your sort of range of acceptable scores. And this is going to bring us on to some of the key challenges when doing performance runs and benchmarking. The first key challenge is that there is fundamental run-to-run variance. So if you go and run the same benchmark on the same version of Node on the same machine once after each other, there's a very good chance that you'll get two different scores. And depending on your environment and a lot of other things, they could be quite far apart. So the first thing you're going to need to do when you're doing some benchmarking is to run your benchmark a good number of times so you can get a good feel for the data, for the range of scores that you see. This is also possibly going to hold you back later on if you go and run your benchmark and find out actually there's a 10% difference between the best score and the worst score. If you're then going to want to try and narrow down a 2% regression, it's going to be quite difficult to reproduce that and to accurately measure. One of the things that could cause these issues is having a consistent environment. So the machine that you're doing your testing on, you're going to want to try and make sure that it's in the same state each time you run your tests. In our team at IBM, one of the things that we do to try and get around this is we reboot our machine before we run each set of tests. This means that each time we run our test, the machine should be hopefully in the same state, so there won't be any leftover processes or anything else like that that could be affecting our scores. And it also means it's very easy for us to get back into that same state. So if we wanted to rerun our set of tests, we can just reboot the machine, run them again, and hopefully the machine should be in the same state. Something else that would help with getting a consistent environment is making sure your machine is isolated from outside interference. So that could be making sure other people aren't going to be logging into your machine and running something at the same time that could skew your scores. If you're running a throughput test that relies on network traffic, you may want to have it on a private network so there's not going to be other people transferring files across the network and potentially affecting the scores of your run. Something else you may want to do would be to interleave your good build and whatever it is that you're wanting to test. And by that I mean that we could run one copy of your good build followed by a copy of the one you're testing and so on. And that should hopefully mean that any interference that's happening on the machine may be alleviated. It's much better than comparing the scores you got from your good build when you ran it 2 months ago. Things on a machine will change even though you think they may not. The final key challenge is the jumping to conclusions. So it's very easy. So you go and do a single run of your good build, single run of your build you're testing. They look the same, brilliant, job done. We don't need to bother doing all those reruns because everything looks fine. You should still go back and make sure you collect a good number of measures so you have confidence in the data. So, some different approaches that you may take towards benchmarking. The first approach could be to do some micro benchmarks. So this could be useful if you're implementing a new API or a new function, or you're making some changes to an API or function and you want to see, have your changes made any change to how it performs? These are quite useful for maybe comparing key characteristics. Some things to be aware of, though, is that even if you go and improve, for example, the buffer API, so it now runs 300 times faster, that may not actually translate into any real-world improvements, because perhaps creating a buffer might be a very, very small percentage of the time spent in a real-world application. Something else that you should be aware of is that when you are micro-benchmarking, especially when you're running on a runtime that uses a JIT or some sort of optimizer, there's a good chance that the JIT could go and optimize away the thing that you're trying to test. So you may not actually be testing what you think you're testing. There's plenty of presentations and videos online of people going through and actually showing what the JIT ends up running. And actually, you think you're testing some API, but actually you might just be testing the performance of how quickly it can go through a for loop, and it might have got rid of the bit you're testing altogether. Another approach to benchmarking would be sort of whole system benchmarking. So this could be where you would be pulling various metrics out of your full application. An example of that might be the Acme Air benchmark, which is one of the benchmarks that we run in the community benchmarking workgroup. This is a fictional airline, and a user can create themselves an account, log in, book themselves on flights, check in, all sorts of stuff like that. And we use JMeter to drive load against that to measure how many requests a second Node.js can serve, along with some other metrics. This is good because it represents a more realistic, real-world approach. The disadvantage is the more things that you're doing within your benchmark, you introduce more room for variance. So there's a good chance that you might get really consistent micro-benchmark results, but when you go and do lots of these micro-benchmarks in a whole world system, you may find that the variance between your different runs increases quite a bit. So you've gone and collected a load of data. What are you going to do now? You think you found a regression. The first thing to do is to make sure that you actually have found a regression. Make sure that you've got a good range of data for your good build and whatever it is that you're testing. Have a look at the variance compared to the percentage regression you think you found. As I mentioned before, if you've got a 10% variance or 10% range of scores for your benchmark and you think you've seen a 2% regression, that's going to be quite difficult when we get later on to trying to narrow it down, because we're going to need to make sure that this regression that we think we found is easy to reproduce to give us the best chance of finding what it is that's caused it. So if we're sure that the regression exists, we then need to have a look at what it is that we actually changed. If it's our application code, one way around, we could have a look at what it is that's changed between our good build of our application code and this one that we're testing. It could be that you've gone and upgraded your copy of Node.js to a later version, in which case we need to have a look at what it is that's actually changed within Node.js. Or it could be that you've just gone and moved your whole stack onto a brand new server that should be running a bit faster, but maybe it's not quite running faster, in which case we need to start looking at what V8 or other platform-specific things are doing. Perhaps it's doing something that we're not expecting. We then need to be able to compare between the good and the bad cases. So there's some tools that we can use. Well, in fact, there's hundreds and hundreds of different tools we could use. I'm going to talk about a few of them. Another option is we could just sort of binary chop our change sets. So if we're looking at Node.js and we can see that in one version of Node we were good, and then in another we were bad, we can have a look at what it is that's changed between those two different versions to try and help us work out what might have caused the regression. So within Node.js, as I'm sure you're all aware, there's lots of different things that come into the Node.js project to provide us with our Node.js binary. There's some native JavaScript things in the lib folder, so buffer, cluster, lots and lots of things in there. V8, if you've upgraded your version of Node, it may well have pulled in a newer version of V8 that could potentially have caused a regression. There may have been a recent security fix that could also affect performance. It could be libuv, it could be a new version of npm npm module that you've pulled in. It could be lots of different things. So some of the tools that we could use, we could look at some JavaScript profilers. So we've got the V8 profiler, and we also got something such as Appmetrics, but there are lots of others available as well. We may also want to use a native system profiler that's not just going to look at V8 and JavaScript, it's going to look at all the other things that are going on the machine at the same time. So this is a micro benchmark that we've been running at IBM. What we do is we go and get quite a large array with 60 numbers in it. We then go in, we've got our for loop at the bottom there, which is going to go and create lots of new buffers from this array. We then go and run this through a test harness, which will keep repeating until we either get a good consistency of data or until we've reached our maximum number of runs. When we ran this on Node 4.3.2, we were seeing operations a second of about 10.6. And then when we upgraded to Node 4.4.0, we saw that drop to just over 6 operations a second. So it's a fair size regression. So these are some of the tools that we could use to try and narrow down what it is that's caused this regression. So the first one is the V8 profiler. This comes as part of V8, and you can expose it through Node by adding --prof to your command line. When you run that, it'll produce a file just as we've got there, isolate a hex number and then v8.log. So you can run your benchmark or your application normally, and then you can go and post-process this later. So in more recent versions of Node 4 and Node 5, you can use --prof process, and that'll go and post-process this log and give it something, put it in a format that's a little bit more readable. There are also some helper modules, for example, V8 profiler, which will let you programmatically enable and disable the V8 profiler. So when I went and ran this on our good build on 4.3.2 and our one that we were testing, Node 4.4.0, we saw quite an increase in the compilation of the from object. So originally we were seeing about just over 23% of the time spent in that, and then when we went up to 4.4.0, this went up to 47%. So it's a fair increase. Can go and get similar sort of data out of Perf, which is our whole system profiler. The output of this would also show you time spent in native system modules and things like that. But again, the big difference between the good and the bad profile was this time spent in this lazy compile. So that's suggesting that it could be something that V8 is doing differently. So we can then go and turn on some extra trace options into V8. So again, we can pass these straight into our Node command line. So we can use --trace-opt and --trace-deopt, which is going to look at optimizations and de-optimizations. On our good case, we saw that we were noticing that from object was quite hot, so we're going to compile it and optimize it. And then in our bad case, we saw that just after doing all that work of compiling and optimizing, we then went and dropped the optimization anyway, and we went and de-optimized it. So that's a bit funny. Another way that we could go and try and find the difference between these, as I was saying before, is just sort of go and binary chop the change sets, which is all right in this case because we were looking at two adjacent versions of Node. But if you were upgrading from Node 0.8 to Node 6, you'd have a few more change sets to look through, and it might take a bit more time. Another option that you could use is something such as Appmetrics, which Andy mentioned about before. Available on NPM. You can go and get all sorts of CPU information, GC, memory, profiling information out of V8. You can either add the information that you want programmatically, like this, turning on when we get CPU information, go and print it out to console. Or you can also connect IBM Health Center to it over the network and then connect directly in, and that also allows you to enable and disable the method profiling as you require. With our regression that we saw before, the actual problem, it turned out, was because we were in the Node 4.4.0, we'd gone and changed how we were declaring the iterator in our for loops in the buffer module, or buffer.js. Originally we were using var and then we switched to let. So we went and issued a pull request to go and revert that change. As it turns out that the V8 optimizer isn't too happy when you have lets in a for loop. This is going to be fixed later on in a later version of V8 once turbofan becomes the default optimizer. But for the meantime, we've gone and changed that back to just having them as vars, so it's just changing the scope of the variable. And when we made that change, we saw the performance go back up to where it was in the previous version of Node. There we are. So I'm just going to talk now very briefly about the Node.js benchmarking workgroup. So the workgroup's been going for quite a while. We got a mandate to track and evangelize performance gains between Node releases. We've got key goals of defining use cases for Node, identifying benchmarks that represent these use cases, and then running and capturing results and reporting them to the community. We've currently got about 13 members, and we have meetings every month or so. We had a meeting on Tuesday, so our next one's likely to be in early May. You can have a look at what's going on the GitHub page, Node.js benchmarking, and you can also see the various graphs for the benchmarks we run in there on benchmarking.nodejs.org. So these are a few of the use cases that we've discussed in the community and we then approved at the meeting on Tuesday. These aren't necessarily set in stone, so if you're looking at this list and saying, actually, my use case isn't there, then come and let us know and we can see where we can go there. So some of the use cases, we've got things such as backend API services. So this is REST and REST-like APIs, typically running over the internet or over public networks. So we're going to want to make sure that Node can perform and doesn't regress in these sort of situations. Service-oriented architectures. So these may typically be private APIs and where things such as very low latency are very important. Microservice-based applications. This may be cases where they use some different types of networking protocols, possibly things such as UDP. So we're going to want to make sure that Node is as successful as possible at transmitting this information. Generating and serving dynamic web page content. So we've got modules such as Express, Happy, Koa, React, and so on. All these modules are very popular within the Node ecosystem, and we want to make sure that things that we change within Node don't go and regress the use of modules such as this. Single page applications, then communicating back to the back end over WebSockets and HTTP2. Agents and data collectors that may be distributed through networks, where we're going to want to be able to update those automatically rather than having to go and redeploy. Node's also used quite a lot in sort of small scripts, or being able to script stuff to run quickly. So in those sort of cases where we'd want it to be using very low amounts of CPU, low amounts of memory, quick startup, things such as that. So all of these different use cases, we're going to be looking at these list of metrics. So we're going to want consistent low latency in our communication, the ability to support high concurrency. We're going to be wanting to look at throughput. We're going to want fast startup time, fast shutdown, and therefore also fast restarting, and also using low resource, so memory and CPU. If you want to have a look at these use cases in a bit more information, in a bit more detail, the information is again on the Node.js benchmarking workgroup. So the benchmarks that we've been running so far, at the moment we've been looking at some quite basic startup tests. So we're having a look at how quickly Node can start up when it's not going to be really doing very much. We've been looking at footprints, how much memory footprint or resident set does Node use once it's up. We've been looking at how long it takes when you go and require a module, both for the first time and also perhaps when it's been cached. And as I mentioned before, we've also been running Acme Air. So we've been looking at things such as throughput, response time, and various footprint measures as well, which we've been taking once Node started up, but before we start driving load, and also after we've been driving load for a while to see how Node scales once it's been doing some work. We've got a few other benchmarks in progress. So we've got some that have been written to look at the performance of the URL module. And we're also looking at grabbing some of the benchmarks which are in the Node.js benchmarking directory and be running those more regularly and be able to graph the results. So as I mentioned before, benchmarking.nodejs.org, I'd encourage you all to go and have a look to see whereabouts we are. We've got lots of charts such as this one. So this is our Acme Air throughput chart. We've been running this since February sort of time. So once a day we go and run the latest checkout from GitHub of 0.12, 4 and master. And then once we've cut node 6, we'll be adding that to the chart as well. Obviously at the moment it's being tracked in master. It's quite a good sign, so we can see there at the top we've got the master branch performing the best, followed by node 4, followed by node 0.12. So it's the right sort of pattern. We want to see newer versions of Node performing better than the previous ones. So how can you get involved? Go and have a look at our GitHub repo, Node.js benchmarking. Go and have a look at what it is we're running, have a look at our use cases, have a think about how you're using Node. If you're saying, well, actually, how I use Node or the sort of things that I run aren't there, open an issue and let us know. We want to try and get as many benchmarks running as possible that cover all the uses of Node.js. That's about all I've got. So if you've got any questions, I'll be happy to answer them a little later on.